two main goals. Um, the first is to step away from the nitty-gritty of computers and software and to look at some of the concepts that underlie what it means to compute. Um, so, in fact, uh, computer science departments in Europe are often called uh, informatics, or departments of information science. And that stresses more about that the discipline is about how information is handled and the properties of information itself, rather than these devices that we call computers. So we're going to talk a little bit about what it means to compute in a near theoretical sense, the fundamental properties of it, and and then I'm going to relate it back to biology and why these concepts are important in modern life science. In the second part, we are going to get into the nitty gritty today. It's going to be a separate video, in fact, but we're going to start with our Studio Cloud, and we'll kind of get organized and navigate our way around the system a little bit, and we'll even look at a few small examples of our programs. Okay, so what fundamentally is a computer? Well, according to the OED, it might look something like, a definition might look like this: an electronic device which is capable of receiving information, data, or input in a particular form, and of performing a sequence of operations in accordance with a predetermined but variable set of procedural instructions, which we might call a program or software, to produce a result in the form of information or signal, which we might call output. I don't agree with this definition. Um, Number one, I'll argue today that it doesn't need to be electronic, and lots of examples of computers existed before electronic devices. Secondly, it doesn't need to be digital. In fact, there's great examples, especially in Russia for some reason, as late as in the 1970s, where they were focused on developing analog computers that don't, don't convert our information into this digital 0-1 formula. So then, what are the fundamental properties that define computers and computation? Well, I'd say that there's three broad properties. Okay, property one, I would argue, is that there is a paradigm of input, algorithm, output. Okay, so by this I mean, for example, if I speak to voice recognition software, that's the input, and it's passed to an algorithm, the translation program, and it takes that voice and it produces the sentence that I spoke in a second language. Okay, so it is the input is my voice. It's captured, then it's recognized and translated and output into, say, a second language like Chinese. Okay, so yeah, three main concepts: input, a transformation of that input to an output for some purpose. Okay, and property two, I would argue, in a broad sense, is a notion of reprogrammability. Okay, by reprogrammability, I mean that the device, the computer itself, can have multiple functions. So I think we all understand that that's really true, right? I mean, if we have an Xbox, then our input may be physical action to an Xbox Connect sensor. The algorithm might be a Call of Duty game, okay, and that's going to produce some kind of output on the screen um, related to the game, okay? But if I get sick of Call of Duty, then I take out the Call of Duty game and I replace it with a Halo game, and that same Xbox system is going to take my physical action and convert it to some sort of, image on the screen that's this fantasy world of, uh, you know, that video game, right? Okay, so the algorithm can change, and I think we all, there's ample opportunities of how you run multiple pieces of software on your phone, laptop, computer, etc. So basically, what's happening there is that program is being replaced in the processor and the RAM, the memory, and it can be switched pretty easily. Okay, and the third property of computation, I would argue, and I think it's necessary. It's just these three properties that are necessary and sufficient. It's that there's a notion of state and memory, right? But really basically the same thing. So let me give you an example. If my input is SANI or TA, and if the moon is blue, the algorithm checks is the moon is blue. So you can think of the algorithm as going outside at night, looking up into the sky, and if the moon is blue, it predicts or it writes to the screen that Sandy beats Mike at cricket. Okay, um, but if the algorithm steps outside at night and looks up at the sky and sees that the moon is not blue, which we would all agree is almost always, if not always, then Sandy will be predicted to lose horribly, right, in a massacre on the cricket, whatever you call it, field or pitch or whatever. So the point here is that the algorithm makes choices depending on the input. Okay, so it looks at memory, which is properties of Sani, or in this case here, properties of the night sky, and that's the input to this um, algorithm. Actually, it's not really Sani; it's the night sky. So then the algorithm, is able to measure somehow that information, and it makes a decision depending on whether it's blue or not, right? So it looks at a state. Another example would be, for example, a weather report as input, and presumably that weather report has a field about the current temperature. So the algorithm says, if it's less than 24 degrees Celsius, then uh, you know the action is to wear a jacket. But if the temperature is bigger than 24, greater than 24 Celsius, then in fact what will happen is that you, it will recommend not wearing a jacket. So in this case here, the state or memory is the algorithm makes use of something that's stored in memory. So it's the weather report or the property of the night sky, etc. That's the state of the universe. It's looking at that and making decisions from it. Okay, so um, I think that's something. All the fact that I claim that these are three necessary and sufficient properties for computation may be a bit controversial amongst you, and it's something that maybe you should reflect on to see if it matches your intuition of what it means to compute and what computers are. You'll notice here that there's nothing fundamental about it being electronic nor digital per se. Um, in fact, something, there's all sorts of aspects in here that in reality in our lives that are not digital in a sense. So it's kind of natural that maybe computation should extend to non-digital ideas. Okay, so then, here we've been saying this idea of an algorithm. So what is an algorithm? We would need a definition for that. So, given a problem, let's say this is your typical computer sciencey like question. So you're given a list of numbers, and let's call that list L, just a name, and you want to find the largest number in that list. Okay, so for example, the input L might have the numbers 6, 17, 4, 39, 6, 78, 4, 2. And clearly, the largest number in that list, just from visual inspection, is 78. Of course, we want to develop a computer program or an algorithm to solve that problem. So an algorithm might look like this to solve the problem. And it's by no means the only possible algorithm, but here's one. So step one is if the list L is empty, then there's no largest number. I think we all agree on that, and you're finished. Step two is assume that the first element of the list, in this case, 6, is the largest. Okay, so we look at the first element and see it's a 6 and say, okay, well, I have nothing else to go on, so let's make that the largest number in the list. Then, for each remaining number in the list, step 3 says that if it's bigger than the current largest number, make it the new largest number. So the next element in the list would be 17. So is 17, okay, so, right. So 17 would be bigger than 6, and so we would make it the new largest number. So when all the numbers have been checked, once we get down here to the last guy, After 2, um, the current largest number is the number we're going to report as the largest in the list. Okay, so this is a really simple, silly example to give you the flavor of an algorithm. Okay, so uh, how would we, let's look at an example of executing that algorithm. If that's our input list, it's the same list as the previous page. It's not empty, so there's nothing to do on step 1. Step 2, we make 6 the largest number, okay? Step 3, for all remaining numbers, whoops, there's a mistake there, in L, um, if 17 is bigger than 6, which it is, so now my largest number currently is 17, okay? Is 4, the next number, bigger than 17? No. So my biggest number stays 17. Is 39 bigger than 17? Yes. So now 39 is my largest. Is 6 bigger than 39? No. 78 certainly is. And then we get no and no for 4 and 2. And so 78 is the largest in the list, and that's what we report back. Is this a computer program? Absolutely not. It's not precise enough to submit to a computer to be executed, no matter what your language, whether it's R or Python or Julia or C++ or anything else. Computer programs require far more precision. Is it a precise recipe for solving a problem? I mean, I guess so, although, it depends on how precise we need to be. So when you guys look at this algorithm, do you see any problems with it? And it would take some discussion between us to probably agree whether it is precise or not, sufficiently precise or not. I think it's precise, but it's easy to make mistakes. Okay, so I would say an algorithm is a self-contained, step-by-step set of operations to be performed. I think it's pretty self-explanatory, except maybe the self-contained. Um, what do I mean by that? Well, it generally, I think the best intuition is that um, when I write down a statement like um, make the next guy the largest so far, we all have to agree what we mean by largest, right? So we're dealing with numbers, so we know when 17, we all agree that 17 is bigger than 4. But what if we were instead using strings or characters and we said like A, B, C, is this bigger or is this smaller than D, E, F? Well, we would have to agree what we mean here by less than when it comes to characters, like words like this. So if we were to say, yeah, well, I think ABC is less than DEF because in the phone book, ABC would be listed before DEF. Um, well, some of you may not know what a phone book is, but back in the day, we used to get like this giant paper book delivered to our doorstep, whether you wanted it or not, and it had everybody in the city's phone number in it, along with their address. And so, if you wanted to find um, Abbott's name, you would look under A, and it would be ordered what's called lexicographically. So if we believe here in lexicographical ordering, then we understand what less than means. But the self-contained simply says that all these kinds of vagaries or places where we might disagree have to be spelled out explicitly. We can't have, guessing going on as to what any symbol or word means in that program. Okay. So a computer program is different than an algorithm. It's a list of instructions that tell the computer what to do in order to achieve some predefined task. So it's like an algorithm, but it has to be precise enough that the computer can understand it. Now, how do you do that? Well, usually we work within a computer language. So that's a formal constructed language for expressing computer programs. It's, like a natural language. There's a syntax and there's semantics. Um, and there's a structure and it's hard to learn and all these kinds of properties. Actually, there's a lot of parallels between computer languages and natural languages. But computer programs have a formal construction to them, and that I think maybe requires a little bit of explanation. Um, you know, I think natural languages also have a formal construction to them. There are rules. Everybody agrees there are rules. But we know that the rules can be bent and we still understand each other. Dialects change words slightly or dramatically, and we still understand one another up to a certain point. That can't really happen in computer programs. One has to stick to a very formal, precise definition of what it means in that language and how to express yourself. Computer programming, then, is the art and science of writing programs in a specific programming language. The only thing I think I need to explain there is that it is an art, and I'm going to sound like I'm contradicting myself from the last statement, but um, programming languages um, are very expressive, and almost anything that you do, any program that you write, could have been written in other ways. And very good programmers who know a programming language really well. Okay, and that itself is really important. I'm a good programmer in some languages, and other languages I don't know enough about those languages to really express myself in a deep manner. It's just the same with natural languages that I could be really good at English and be able to express, very deep, esoteric, subtle thoughts I'm having, but I certainly can't do that in French nearly as well. Okay, and so there is an art of how to express a computer program. It's a formal entity, yet being expressive and clear and documenting things well and organizing your programs well is an art. And there's a lot of value to that. And you guys are going to learn not just the science of computer programming, but a little about the art of computer programming as we move along too. Okay, so here's an example of an R program for our biggest number problem. We call it find max. This is just for your interest's sake here. I mean, I think already you'll be surprised at how much you understand of this little program. So find max is going to be a function, okay, and um, this takes as input this list L that we've been talking about. And if our list is empty, it has length 0, then there's no real big number, so there's no biggest number, so I just return a -1. Okay. If the length of my list is just one element, it's just one number, then that one number has to be the biggest. So I just basically, this is notation in R for accessing the first element of the list. So I set my biggest number, I return it. It's like telling the user the biggest number is the first element of list because there is only one. Otherwise, now you can start to see step 3 in here. The current largest is set equal to L1. Okay, so I'm at the beginning, I just make the first element to be the largest. You'll notice some weird things like this underscore here. Why do I have that? That's because this is called a variable, this current largest, and I can't use a space. Our demands that my variable names be contiguous. Okay, that's common. You've seen this a lot, I think, out there in the names of files and um, in other scenarios with just operating systems, etc., where you're forced to use underscores, etc., to keep things together. Okay, and then you could ask, well, what does this symbol here mean? And that's read as assigns to. So I'm assigning the first element of RL to be the current largest. That was in the description of the algorithm. We said assign the current largest to be the first. And then we see this statement like for, and basically what we're saying here is that for each remaining element in the list, from the second element all the way down to its tail, if that guy is bigger than our current seen so far, then we make it the current largest. Okay. And after this completes, after we run through the list, we return whatever the current largest is. So you know, at this point, I don't expect you to understand, of course, this R program. You haven't learned how to program yet. But I think intuitively, you can start to see some patterns of how I've went from an algorithm, kind of an inherently natural language description of the solution to the problem to this more formal description. And this program would work in R. Okay, so let's have a little bit of fun here and um, you know, try to argue for or against whether these objects are fit the criteria of modern computing devices. Okay, so this is an abacus, and an abacus adds two numbers together, okay, by basically you moving these beads up and down along these rods. I don't know, I'm not sure I completely remember uh, how an abacus works. I think I did at one time. So we could have a long debate about such a simple object. Is it really an example of a modern of an early computer, or where does it fail to, if it does, with the definition of modern computing? So let's go through um, these three properties that I proposed as being necessary and sufficient. I'm certainly open to discussion in the lecture, um, and I'm happy to hear dissent. So, but let's start here. So, is there input? And I would say absolutely. The whole purpose of a abacus is to add two numbers together, x and y. So clearly there is input. And is there output? Well, because we're adding x and y together, the abacus would not be working if it didn't actually output x plus y. Now the algorithm. Is there an algorithm? Well, absolutely there's an algorithm in some sense, because for it to work, it has to know, or the system has to know, how to take x and y to produce x plus y. Now, does the abacus know how to add two numbers? No. I would say that the individual who owns the abacus is shifting the beads up and down according to an algorithm, but fundamentally, the human is executing the algorithm and not the abacus. The human is moving the beads, but also they know, he or she, what the algorithm is on this particular infrastructure. So I think we would expect from a computing device that it actually computes the algorithm, right? It executes the algorithm. So, for example, if the abacus had a mouth but no arms, then if it was telling the human, okay, hey, human, go move the one, two, three, four, fifth um, rod, this bead up to the top, up to here, okay, and move this bead down, okay, and then blah, 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 blah. It keeps giving instructions, and the human was simply the arms of the abacus, then I would say yes, the abacus is in fact able to carry out the algorithm because the human's contribution is purely mechanical and not intellectual in any way. Be careful with intellectual, but it's the human's not carrying out the algorithm. The human is simply a kind of mindless device that moves beads up and down. But of course, an abacus doesn't have a mouth. And so I think that the answer is that this is pretty sketchy, and abacus doesn't really have a concept of an algorithm. But what about notion of reprogrammability? The idea of an abacus is that it takes two numbers, x and y, and adds them up. Um, I'm not sure if you can do subtraction on an abacus. If you could, then and the algorithm could change, then maybe you could make an argument that it is reprogrammable. Or if you could do multiplication on the abacus, then and that would be basically that infrastructure, well, that we see here, the rods and beams, the beads, and the frame. If that was enough, then one could maybe argue that it's reprogrammable. Again, though, is that the algorithm isn't actually in the abacus. The abacus is just a handy infrastructure for the human to actually execute the algorithm. So I would say it sort of fails on this front here, right? Okay, what about notion of state and memory? There I say yes, it does, it definitely. I mean, if it takes as input X and Y, um, you know, if it's going to add Y to X, then it has to remember what X was. And so by moving these beads around, you do encode space. Now it's not electronic, but by moving these rods up and down, sorry, these beads up and down on these rods, right? Um, you are encoding a scenario or a state or some kind of condition of the universe, right? So I do say yes. So I would say overall that's problematic. That's definitely reprogrammability is problematic, but notion of state and memory, the abacus has kind of got it right. Okay, so here's a second example using a calculator, and I like this one because it is electronic and it is digital. If we go back to that OED definition, Oxford English Dictionary definition at the beginning. So, does a calculator have input? Absolutely. Does it have output? Absolutely. Um, does it have an algorithm? Yes, it has multiple, right? We have plus, minus, times, divide, etc. So I would say it definitely has an algorithm, and the human here is not carrying out those calculations. It's encoded in the device. Now, is there a notion of reprogrammability? Um, okay, you know, that's the issue, isn't it? Um, we are stuck with the options that are given here. So it wouldn't be easy to do exponentiation on this calculator, except to do 5 times 5 times 5 times 5 if we wanted 5 to the fourth. And the square root, well, we'd have to figure out how to take the square root of 7 um, back in the day of, grade school math or high school math when we learned how to do that, the algorithm to do that. So that algorithm is not present there. Or let's say a really obvious example is that it would be difficult, or we don't have the algorithm there for the sine or cosine curves. So it's not really reprogrammable. It has multiple functions, but there's a fixed number of such options. Okay, um, and there's several algorithms, but it's not fully reprogrammable. And so, whereas this issue is like that property is fully fulfilled, I'd say it fails pretty miserably on reprogrammability. Does it have a notion of state and memory? Absolutely. Again, like the abacus, if you want to add y to the integer x, then you need to have x in memory somehow. In fact, then you have these kinds of fancier things that I struggled for years to understand how to use, which was to add numbers to memory and to clear the memory, etc., and to read the memory. And so there's a little bit of ways to extend how much memory there is, but it's limited still. So I'll put a little mark there to say that it's not fully um, able to, encode lots of state memory. There's a little bit of functionality in that direction. And of course, like we're getting close to a modern computer, though, in many ways. Okay, so, and what about this, the watch, right? I mean, this is um, one of the most complex entities that humans ever made before the computer. It was recognized as that. And the amount of engineering that goes into watch, precision, but also the computational properties, right? So let's think about a watch for a second. Is there an input, an algorithm, and an output? Input, I think you might agree, is hard to think about. Is there an output? I would say yes, because when we look at the watch face, we see the time, right? I'm talking here about analog watches and not a digital one. So there is an output. It is telling us the time, right? Is there an algorithm? I'll argue yes, but it's not a digital algorithm. It's really an analog algorithm. It's encoded in these gears, right? But there is a program to that. There is a structure, an engineered structure that makes these gears interact um, in such a way that they exactly mimic, or very close to exactly mimic, true time. So that I think is um, and it's executed by the watch. So that algorithm is executed by the watch, not like the abacus that doesn't execute its own algorithm. Is there an input? I don't think so. I mean, maybe you could argue that when you set your watch, that is the input. All right. So, but I think it's quite weak on this notion that there's an input per se. It's just constantly computing an algorithm, an analog algorithm that produces an output. But, is it important to have an input? I'm not sure. I mean, there could be other things. Like, for example, you could have a computer that measures seismic activity, so it wouldn't really ever need to be asked to start measuring seismic activity except once when you turn it on, and it would just continually measure, and it would, flash a red light when it saw an earthquake starting or something, right? So maybe input could be removed from a necessary and sufficient property of computation. What about reprogrammability? Well, I would say also overall, I'd say it's pretty good with a tiny little X on the thing for that property. Now, what about reprogrammability? I think, yeah, no, it fails. I don't think we can really think of it as being reprogrammable. I think, we could, change the time when we move time zones or something, or if we went to a different planet. Um, if that other planet was exactly like Earth in terms of the size of the sun and distance to the sun, or our time around the sun, that would be, yeah, that's not it. It's not the distance, right, or the size of the sun. It's really just the time it takes to go around the sun along the circumference. So if it was exactly the same, then that watch would work there. But you couldn't reprogram it without, a lot of heavy duty work to re-engineer it. So I would say no, it fails on the reprogrammability front. What about the notion of state and memory? Um, in a very, I guess I would say it's a very vague. Um, I guess because it's analog, it's saying like, well, it's now 4:55 p.m. and 16 seconds, and so now it's 4:55 and 17 seconds. Oh, and now it's 18 seconds. So if there's memory, it's just the fact that it's 1 second later than the previous time interval, right? But it's not really uh, ever, you can't really make a decision on that, right? On that state. There's no decision making per se. Okay, so I'd say overall, it's not really a computing device per se, although it has aspects of it. It's not a modern computing device. Okay, so what about this, right? So I mean, I like this picture. So firstly, what is that, right? Because it's not at all clear to me. But I will tell you that this object was considered to be the most complex object created by humans before the computer. Okay, more so than the car or rocket ships or anything else. This was really considered to be the most complicated entity that humans had designed, right up there with the watch, maybe even above it. And the answer to this is it's a organ. Okay, so the previous picture was the back of that organ. Okay, okay, so um, that's weird. So let's go through that one because this was something that was considered so complex as a human creation. Is it a modern computing device? Well, is there input? Absolutely, there's input. So there's two inputs on the, well, really three inputs on the organ. There's the keys here, there's the pedals down here, and there's many of them often, or so that's the pedals there. And also there is these toggles. So these toggles change a system of windpipes that change the tone and bass and vibrato and all sorts of um, musical or sound properties of the air going through pipes. Okay, so I can press the same C key, which is say right there, with certain keys flipped up and other keys flip down. And if I hit that same key again, but I change them and I toggle these guys in the opposite direction, I'm going to get a different sound because the air travels down a different set of pipes to make that sound. Okay, so there's input, and the output I think is pretty clear. There is definitely sound that comes out, so there's input and output. Is there an algorithm? Well, um, that might be the weakest part, but in a sense it does, because when you press a key or a pedal and a key, what you're doing is basically sending air down a certain set of, a very specific set of pipes. And with those toggles, that changes those pipes too. So, you know, it might be a very simple algorithm, but it's, you know, oxygen or air, I'll say just air because there can be many things in the air, versus electrons, right? So, you know, let's be careful here. I mean, a computer, when I press keystrokes or I hit return and I run a program, I'm basically sending electrons down a wire. And in an organ, when I hit keystrokes, or pedals, I send air down a pipe. So, I mean, is it really fair to say that the algorithm is not present in the organ just because it's air and pipes versus electrons and wires? Now, I do think that the algorithm is very simple in the sense that there's no complicated logic per se. And we'll come back to that in a second. But I would say that there is a weak notion of algorithm in here. Okay. So notion of reprogrammability, I'm not sure that that really, uh, you know, that really, it really makes that cut there, because the organ can't be reprogrammed to do other uh, jobs. I mean, even if you just say, well, what about different noises or different, let's say, so it sounds, not noise, but nice sounds, it would still require re-engineering the pipes on the organism. And that's not really kind of reprogramming in the sense that, you know, if you want to make it sound like a violin, maybe it's possible by doing all sorts of fancy woodwork, but it's not easy to do that in the organ itself, unless there is a set of toggles that make it, you know, happen to make it sound like a violin. So I'd say reprogrammability is out. And what about the notion of state and memory? I think that there is, and the pedals together with these toggles um, really do encode a notion of state. So, you know, if your vibrato is on and your bass is off, that's going to get a certain algorithm of air going down pipes is going to be executed in response to that. So you can think of it as saying, like, if my vibrato is off, then make this sound. If my vibrato is on, make that sound instead. So I do think that, you know, this, the organ has a notion of state and memory. Okay, so I want to now bring this back a little bit towards biology, uh, especially this term systems biology, which I like a lot. But why am I putting a picture of IKEA up there? I think we all probably have experience with IKEA at least once or 1,000 times in our lives. Um, so, what does then IKEA or modern commercial enterprises have to do with computing and what we've just talked about? Maybe it's a little bit difficult to see from this picture, but what about if I put up the IKEA maze? I can tell you it's very intentionally designed. A lot of thought goes into how that layout is made. In fact, I know somebody who is responsible for layouts in Montreal IKEAs. They're looking for a very specific user experience, somebody showing up at the store. Okay, so you know, clearly IKEA is not a computing device in a strict sense, but there's a concept there that I really think is important um, in biology. And I'm giving here an example here from commerce, but um, really that I'm trying to say that this idea is now pervasive in our society. I could have easily also used an example from Ford Motor Company and the first assembly lines at the turn of the century before the first electronic computer. It's this thinking of that's very algorithmic uh, that goes into manufacturing and sales and all sorts of aspects, medical treatment, our healthcare system, um, getting your license. What we might call bureaucracy, right? Organization in companies and governments and entities. Um, it's algorithmic, isn't it, in some sense? I mean, isn't there a property of it? So is this IKEA experience an algorithm? Does it have input in the sense that we've been talking about? Well, aren't we kind of the input to the IKEA store? Aren't we the people the input in a way? Um, or maybe more accurately, isn't our aren't our needs for inexpensive yet uh, you know Scandinavian simple styled furniture, um, isn't that the input that they're addressing? They've recognized in us a need, um, and they're providing this receptacle to meet that need. So um, I'm not sure exactly what the input is, but somehow it has to do with the fact that we're showing up at a store and we have desires, right? And they want to fulfill those desires, right? So is there an algorithm and is there an output? Let's think about output first, okay? So um, the output really is, I guess, us purchasing things, right? So we're happy and IKEA's happy because they've sold a lot of well-designed, simple Scandinavian furniture, right? So the output is not really information. It's more about um, satisfaction of the user's desires, right? So it's satisfying the input. Um, Now there's a byproduct there, which is profit for the company per se, the survival of the company. That the average computer doesn't have that dimension. But is there an algorithm? I I think there is kind of something in here that's quite algorithmic in that they have understood our needs and they understand their needs of making profit and they have designed a very specific maze through that store, a certain formula that we have to walk through almost like rats, um, where we fulfill our wishes of what we need, and maybe we still pick up some extra candles, napkins, and a couple dozen wine glasses, right? So things that we didn't really know we needed before we got there. So I wouldn't say, it's really kind of the classic computing device, of course, but I do think that there is a concept there of algorithmics being applied at the um, commercial level. Is the notion of reprogrammability? Well, again, I don't think it's like we can, um, software's reprogrammability, computers' reprogrammability that we think of, electronic computers at least, is that we can change the software and do different things. Here, I think that what they have is a notion that they can change um, the layout of the store. They can change the what do you call them? The presentations or I've lost the word for it here, but the exhibitions or displays according to the input's needs, right, or desires, or what they think would appeal to us to increase sales. So, they could sell cars tomorrow, and it's not the craziest thing. They can sell meatballs, and they can sell appliances now, and they can sell entire kitchens. They could sell, rocket ships tomorrow, for all I know. So, I don't think that there's anything special about the store that disallows it from being used to sell different things. So there's a slight notion of reprogrammability, which is, I guess, would say is flexibility to satisfy customers, right? I don't know about notion state in memory. Um, I think, part of the experience when you go into these large systems is that uh, you're given choices in front of you that they've optimized well. When you buy a mattress at IKEA, there are levels in quality and price, and they've thought these things out so that the input can decide at what level they should purchase. I'm not sure that's entirely state and memory, but I think somehow um, it's the way that they present things that place us in a certain state uh, that we really feel we want to buy yet another kitchen pot scrubbing device, right? Because they're incredibly good at suckering me into those kinds of things. Okay, so uh, maybe that's not the most convincing example. I don't know to you, but I hope that you get the flair that um, uh, modern commerce, modern government, modern healthcare systems, the individual is kind of input, right? And they design an experience for us. When we go to get our driver's license, we take a number, we sit down, we go up and we present certain forms. We sit down, we go back to another desk, we get a picture taken, we wait, we go back, we sit down, it's developed, et cetera, et cetera, et cetera. I mean, it's so boring that it's unbelievable, but that's the way those systems are designed to efficiently process the person. So of course, there's other constraints besides, there's many constraints about why the layout or the design of a hospital or IKEA or a car factory assembly line is the way it is. It's not just as simple as the input of the user, but it has to do with also profit and speed and the overall, efficacy of the system. But people do, when they sit down, they do see these things as systems. And I think as a point of reflection for this lecture is for you to think about a little bit about what that looks like in biology and how biology is also becoming more systems oriented. I won't go into it here, but an action item that it'll come up in an assignment is to look at what's called the ANTIKYTHERA device, which was built thousands of years ago and used for uh, um, directing boats for navigation and boat systems in the Mediterranean. And I put the link both here and in the notes, the class notes from today's lecture for you to take a look at. And also it's in the reading. And so I ask you as an exercise to ask whether this is a computing device, and we can discuss it in the lecture. Same, there's something called the shadow board. You can watch a little bit. There's a YouTube video here from the Canadian series called Vikings, which I really love that series. I think it was great. It starts off describing two Vikings um, uh, when one has discovered a sun shadow board that allows them to find true north, or where the sun is, sorry. They can find where the sun is even on cloudy days. And this technological advancement allowed them to then invade, for example, England, and travel further to France and to the Mediterranean because they could cross large open bodies of water that weren't easy to navigate beforehand. So I ask you also to take a quick look at that little video, get the idea of what the sun shadow board is, and ask yourself as an exercise where it does or doesn't fail as a modern computing device. Okay, so computation has been around for a long time. I ask you to think a little bit about um, what kind of computers have existed through times, especially after you look at the sundial and the Antikythera and some other items I put into the reading. Um, consider the three fundamental properties of computation. I'm happy to discuss this in the lecture, and we can argue. I'm open to dissent. Um, I would like you to think about how these kinds of concepts have drifted already into the life sciences. And there's some additional links and information in the class notes from this lecture. Okay, thank you very much for your time.